All right, let's jump right into it. Welcome to today's Explainer, where we're going to decode the exact framework Cambridge examiners use to grade the special purpose registers in the 9618 syllabus. And today, we're shining a massive spotlight on one in particular, the accumulator, or the ACC. Now, if you're a student or honestly just someone fascinated by computer architecture, you know this topic can get kind of tricky. But today we're opening up the insider playbook.
So, I want to start by throwing this question directly at you. Why do students consistently lose marks on multi-step accumulator calculations? Well, multi-step calculations and method marks are notorious stumbling blocks. It's really not just about knowing what the ACC is, it's all about the process. You know, a lot of candidates just freeze up, or they kind of skip steps when the calculations get complex, and that is exactly where the marks just slip right through their fingers.
Get a load of this. A senior examiner literally stated, "The difference between a B and an A star in computer science often comes down to how well you understand the accumulator." I mean, that sets the stakes perfectly, right? Mastering this specific register isn't just some box to check on a revision list. It is absolutely crucial for securing those top-tier grades.
Okay, so here is our roadmap for today. First, the ACE differentiator. Second, top examiner traps. Third, the procedural framework. And finally, number 4, critical analysis strategies. Let's get to it.
Starting off with Section 1, the ACE differentiator.
The absolute most crucial thing to grasp here is that the accumulator isn't just a rote fact you can just blindly memorize. Cambridge defines it as a theoretical architecture. So what does that actually mean for us? It means it rests on precise definitions, causal relationships, and integration with totally different areas of the syllabus. For example, when you execute an assembly language instruction, like loading a value, adding a number, and storing it back, the ACC is the beating heart of that entire causal chain. You really have to use logical, structured reasoning and actively reference those cross-topic connections to show the examiner you truly get how it functions.
And honestly, this brilliantly illustrates the divide between your average candidate and a top-tier one. It's superficial breadth versus analytical depth. An average student might know a little bit about everything, right? That's superficial breadth. But the assessment framework heavily prioritizes analytical depth. The top-performing candidates showed this deeply connected conceptual understanding that they can actually take and transfer to completely unfamiliar contexts. And that's what gets the A star.
Moving right along to Section 2, Top Examiner Traps.
Cambridge principal examiners have explicitly warned us about 3 major pitfalls. First up, the classic trap, using the wrong formula or algorithm for the specific context of the question. Second, students constantly, and I mean constantly, forget to check boundary conditions and edge cases. And third, giving generic textbook answers that aren't tailored to the actual scenario given in the exam. You literally have to be hyper-vigilant about the specifics of whatever scenario they throw at you.
Guys, I really want to emphasize this examiner alert. Candidates consistently confuse key terminology. If you take away just one immediate, actionable fix from this whole explainer, please let it be this. Always, always define your terms before diving into an extended response. Don't just assume the examiner knows what you mean or that they'll give you the benefit of the doubt. Prove it to them. Define your technical terms clearly right from the jump.
All right, let's look at Section 3, the procedural framework.
This 5-step method mark strategy, this is your blueprint. Examiners actually award method marks specifically for following this exact procedural flow. Step 1, deconstruct the question. Step 2, extract the relevant data. Step 3, select the proper analytical framework. Step 4, execute your calculation using crystal clear notation. And Step 5, present your final answer using the correct terminology. If you follow these exact steps, you secure those process marks, even if, say, your final arithmetic ends up being slightly off.
Now, algorithmic thinking goes completely hand in hand with the ACC. The essentials you need to focus on are step-by-step decomposition, choosing the right data structures, efficient code implementation, and of course, rigorous testing. Think about it. If a question asks you to trace a loop that is continuously adding or modifying values in the ACC, this kind of structured breakdown is entirely non-negotiable. It is exactly how you prove you don't just know the theory, but that you can actually build the logic step by step.
Similarly, executing data interpretation follows a really strict path. First, you extract the data from whatever binary representations they give you. Second, you perform the necessary accumulator calculations. And third,
And guys, this is the one people always forget. You have to draw evidence-based conclusions. Seriously, don't just leave a floating number on the page. You have to explain what that number actually means based on the hard evidence you just calculated.
Almost at the finish line here. Section 4, Critical Analysis Strategies. So, how do top scorers actually evaluate? Well, they don't just solve a problem, pat themselves on the back, and move on. They actively consider multiple solutions. They analyze the trade-offs of using, say, one algorithm over another. They aren't afraid to acknowledge the limitations of their chosen method, and they make sure to justify every single decision with solid evidence. This high level of evaluative thinking is exactly what transforms a good grade into an outstanding one.
When an exam question specifically asks you to compare, remember that comparative analysis requires identifying both similarities and differences. You must use comparative connectives to show the relationship, support every point with evidence, and ultimately draw a conclusion about their relative importance. It's like a balanced scale, right? It's not just a bulleted list of independent facts.
Evaluating the quality of an algorithm means you have to analyze specific metrics, especially when those algorithms are interacting heavily with the ACC. Time complexity, that focuses on execution speed. Space complexity, that's all about memory usage. And edge cases, those test the absolute performance limits of the system. You have to be able to weigh the effect of every single one of these on the overall performance if you want to score maximum marks.
So, to summarize your macro-level exam strategy for practical application, design your algorithms, implement your solutions, test them thoroughly, and finally, evaluate their performance. This continuous loop is how you develop true programming mastery, and it's how you show the examiner you have complete and total command over the special purpose registers.
I want to leave you with this final, kind of provocative thought. The next time you sit down with a past paper, ask yourself, are you going to treat the accumulator as just a basic definition you need to memorize? Or are you going to use it as the strategic analytical framework that actually secures your A-star? Apply these insider strategies, watch out for those examiner traps, and show them the analytical depth you are truly capable of. Thanks so much for joining me on this explainer, and keep learning.